Hello and welcome to the world of NDE 4.0. My name is Johannes Rana and today is a great day because today we will get to what in my eyes will be the next generation of ultrasonic testing. We will get to reconstruction of ultrasonic testing. So kind of like, I guess everybody knows it. If you do an X-ray or you could do a computed tomography. Either you get that 2D image or you get a volumetric image out of it using voxels. Now something similar is actually possible for ultrasonics. And one way of doing it is called SAFT, Synthetic Aperture Focusing Technique. And actually I had the honor of working on a SAFT product, on a SAFT project, which actually developed SAFT for a commercial application on large rotor forgings. And that project that was really successful, and also in the future I will show you a few of the details of that project. But now let's get started with the basics of SAFT, or how we also like to call it, the basics of ultrasonic computed tomography. Now, we already talked in the videos in the past about manual ultrasonics, how you could do sizing with manual ultrasonics. We also talked about phased array. We then came at some point to automated ultrasonic testing, where we have the component, we scan the component using some mechanics, we collect all of the data, and then we can analyze it using A, B, C scans. But with all of that testing, whether it's manual or automated or phased array, we are facing about the same challenge. Now, if let's say we have an indication in our component, like you see it here on the left side, then if we do the inspection, we put the probe on the part, we get a reflection of that indication, and what we do is we take the position of our probe and we take the length from our probe to our reflection. And this is what we draw on our inspection result, our B scan, let's say. And we move the probe. Again, we find the indication. This time, the sound path is a little bit longer. The signal will be a little bit weaker because we do not find it directly, but we only find it under an angle. And we find it at a different probe location. So we mark it again. And once we do that several times, then we get those typical crescent shape indications we know from our ultrasonic results. And we get those with manual inspection, we get those with automated inspection, we get those with conventional UT, and we also get them with phased array. Now you can already see, and I'm coming back to that a little bit later, that what we know with ultrasonics, we know the length of the way from our probe to our indication. But we do not know the position of our indication within the component. And if you think about that, and if you compare it with X-ray, if I just do an X-ray, I exactly know the position where I see my imperfection in the material, but I don't know the distance from the surface to that one. And with the X-ray computed tomography, what I do, I collect the data all one time around the component, I put it into some calculations, and with that I can find out not only the two-dimensional position of my indication, but also the distance from the surface to that indication. With ultrasonics, vice versa. We know the distance, but we do not know the position, or we are lacking the position. And because this is the fact, our indications look like this. But that's not what we want to have. We want to have actually, kind of a focused indication instead of those crescent shape indications. So how can we get there? And one way to get there is called synthetic focusing. So what's the idea behind that? Now, what we have, we already know that our indication has to be on that, yeah, semicircle or in that circle shape. We also know it will be on that one. And we also know it will be on that one. And if we see those three, they actually intersect at exactly one point. And that's what you can do. If you do an ultrasonic inspection and you have your probes, then just take something, mark your circles, and you will find where they intersect, and that's where your location will actually be. You can do that. But for a computer to do that, that's not the most straightforward or not the fastest way. For that, what we do is we actually, we create a grid. We establish a grid on our surface. And what we do in every single volumetric element, which is also called voxel. So we have pixels. Pixels are picture elements, and voxels are volume elements. So about the same as a pixel, but just in 3D. So we divide our volume into thousands of volumetric elements. And for each volumetric element, we add up all the signals going through that element. So let's say we pick that element here, which is right next to our indication. And here, if we add up all our signals, we see that, they are adding up. They are making our signal bigger and bigger and bigger with every single shot. And that's called constructive interference. And what we do, we actually take the high frequency signals, not the rectified signals or something like that. And if we take another location, let's say this one, and we'll look at all our signals, and we see, nothing actually adds up. And what that does is actually, it converts what we have seen here, this crescent-shaped indication, with a lot of math. So we calculate actually that formula for about every location, for every single voxel. But what it does is it creates this signal out of it. And for me, it's a game changer. If we compare this with this. Now, what we did in that project was not just for a single component or for some R&D. No, our project was for the inspection of rotor forgings. And you can see an earlier me standing here next to those forgings, and you can see the huge size of those forgings. Actually, an inspection of one of those forgings with ultrasonics takes about 8 hours, sometimes perhaps even 10 hours. And if we take a shaft into account, then it can be even weeks of inspection time. Now, we do that inspection, and classically, if we've done the inspections, and those inspections, we use conventional probes, we use phased array probes, we use all kinds of different things to accommodate for different indication types. But once the inspection is finished, we're getting results like this. And what we can see here is we see a number of defects in that component. But it's not, we can see here those 3 big ones, but there is actually also one which is here right next to the ID. Do you think you could identify that indication close to the ID with your eye, doing a manual inspection or even doing an automated inspection? Most likely your gate will end right before your back wall. And meaning that, most likely it will be tricky to find such an indication. Or if we look here, there are 2 tiny indications right here. And we can also see here all the blue here in the background. That's our noise. That's our noise we see in our signal. Now that's the classic UT, where we used some phased array technique to actually record all of that data. And then we took the same data and put it into our SAFT pre-processing algorithm. And that's the result we got. You can see, yeah, those here, those are our indications. You can see this is now really giving an image of our indications. The lateral sizing capabilities of SAFT are about 10 to 20 times the sizing capabilities we can get with our conventional or phased array technologies. Also here, that indication, which is close to the ID, if I zoom in, it's very clear that there is an indication. Also, the two tiny ones around here, if I zoom in, it's very clear that we find them. And look at all that noise. All that noise is gone. Now, you might say, yeah, SAFT is not a new technology. And you are completely correct. SAFT goes back actually to 1967 with the invention of the so-called synthetic aperture radar, SAR. And in 72, there was already the first optical imaging system. So we could say 72, we had the first implementation for SAFT. But it was using optical elements and it was all analog and was really complicated to use. And what I find interesting, back then they wouldn't call it SAFT. They called it SAUI. And I'm really glad that they changed the name, because if I take the abbreviation SAU, and being German, SAU is the same as pig in English. So I'm pretty happy that they changed it to SAFT. Even that in Germany, SAFT also has a different meaning. SAFT actually means choose. So you can see some of the jokes coming up in the German audience. Now, 76, we get the first digital synthetic aperture ultrasonic imaging. And there was a lot of work on SAFT over the years. For example, by the group of Professor Langenberg and a lot of others. And then in 2010, we took this technology and we developed an algorithm which is good and fast enough to use it in a daily production in a steel plant, in a forging shop. And we did that together with BAM and Siemens. Actually, it was mainly for the use for Siemens. So clearly that Siemens was in part of that. Now, we already talked a little bit about, the noise. And we could see that here, the noise, we really had a lot of noise in the classical UT, and we have, reduced noise or nearly no noise with SAFT. So where does that come from? Now, number one, if you do averaging, so you take 10 shots of the same location, then actually your signal or your noise level will drop by a factor square root of 10. Now, with SAFT, as we are adding up multiple different positions of our probes, actually, we are doing about the same. We are averaging. It's an intelligent average. So also our noise level goes down by the square root of n. Now, that's only true for noise, which is stochastic, which is random. But we also have a different noise type. That kind of noise type that comes mostly from electrical signal floating around your production environment. But we have a different source of noise, and that's the grain structure. And the grain structure is not stochastic, it's not statistical, it's not random. It is every time at the same location. So by averaging, I can only reduce that stochastic noise. I cannot reduce the grain noise, but I can do it with SAFT. Because usually what's happening with conventional or classic UT is you take kind of all your reflection out of a certain area within your beam. And that's what you kind of compress into one A-scan signal. And you can, if you just count those black dots and every black dot being kind of a grain, we have 3 of them within that gray area. So you can already see that kind of noise we are creating with that. Now, with our synthetic focusing, we are actually only taking into account the signal coming out of one of our volumetric elements, out of one of our voxels. And that's way reduced. So we are only counting 1 dot, 1 grain, instead of 3. And what we found out in reality, it's about a factor of 5 we get in signal to noise ratio improvement by going from classical to SAFT. So we can already see the 2 main benefits of SAFT. Number 1, a better spatial resolution, a way improved spatial resolution. And also number 2, a way improved, noise level. Isn't that such a huge step? I'm still seeing those pictures. I'm still really, baffled. Now here, one more time, a little bit zoomed in, the improvement of our lateral sizing. And now you can even see better that small, tiny indication, which is here close to our bore. And what I can do, for the SAFT, what I take is, I take a normal ultrasonic testing equipment. Best is I do some automated scanning. I do automated scanning. I take my classical or conventional probes, or I can use phased array. I can use whatever kind of data source I have. And I use unrectified high frequency signals. That's what I put into my algorithm. Then I do my reconstruction. And after I have done my reconstruction, I can actually use all kinds of different data reduction sources to keep the data volume down to something which is manageable. Because you can imagine the raw data can get pretty big with SAFT, but you don't have to actually, keep all the raw data. It's better to keep the reconstructed data because there is so much more information in it. Now, more information. There is a lot more information on this topic, which we published. A couple of, or 2 information sources. Number 1, we have done a video, which was kind of professionally recorded video with a director, with a cameraman, and all of that. And you can find the link to that video right here. And I will put the link to both the link to the German and to the English version down in the description. Up here, you will find the link to the English version. And that video was actually recorded by Siemens and put on the Siemens YouTube channel. And I think it's a really good video. So I guess you all should be watching it. And if you're more interested in the details, then get online and buy that paper we wrote about ultrasonic computed tomography. This is giving a lot more details about the automated data recording, about the SAFT principles, about the benefits of SAFT, about the benefits of our implementation, about the benefits, or the basics of the real improvements we gained with it in numbers. And that paper actually was really successful here with the Steel Research, and they actually took one of the images out of that publication and put it on their front cover. And that's a SAFT reconstruction of a shaft, of a large shaft. And you can see actually those indications here within the shaft. That's also kind of what we call it, a transparent shaft. So, thank you for watching. If you have any comments, if you have any questions, feel free to leave them down here in the comment section. Next time, I will take this topic one step further. Because currently what we have is we have a SAFT solution which gives us a better spatial resolution and which drops the noise level. But what we need with ultrasonic testing is we need sizing. And we will see in the next video that sizing by counting voxels, that's possible, but actually not sufficient for our application. So we had to go a couple of steps even further than what I showed you today. And that's what I will show you next time, our approach for the so-called, what I call quantitative SAFT or QSAFT. And for sure in future, I will also get into, this was now, SAFT is taking one probe, recording that signal back and forth, and then taking the overlap of the different probe positions. But there is another method. There is one where you take a phased array probe, you shoot with one probe element, and you receive independently with a lot of different probe elements. And then you take all those different sound paths and you put those into a calculation. And that's called TFM. It will take, I guess, 2 or 3 more months until I get to TFM, but we will get there. As usual, you will find more information in the description. I hope you like this video. I hope you subscribe to this channel. I hope you give me a thumbs up. I hope I will see you soon. So thank you for watching. See you soon. Thank you and bye.